All right, this will be our second segment for our week 4 lectures. Um, our work is primarily going to be working on system efficiency. So the 3D drafting and drawing gets us started, but what we really want to do is do some of the electrical measurements, mechanical measurements, and try and characterize and learn what we can about this pump and how well it works. So essentially the motor and pump is a combined system. The system characteristics include, for the motor itself, it has electrical energy input, and so it has 2 leads where you'll apply a voltage and the motor will start spinning, as with any motor on an RC car or whatever you happen to have them running. So that produces a rotational energy output on the shaft that happens to be sticking straight down on this sample. Now the pump, on the other hand, takes rotational energy as the input and produces mechanical energy output in the form of moving the water. And so in this drawing we've got the water coming out the sides. Of course, for the pump purposes, it was drawn in the face, up through the pump, accelerated, and sent out the side. And so what we want to do is look at the overall system efficiency, because we don't really have a method for measuring that rotational energy that comes out of the motor, yet is as shown as the input for the pump. And so we're going to take a look at the whole system efficiency rather than trying to find the efficiency of any one piece at this point. So the total system is going to have an electrical energy input and a mechanical energy output. And so again, if you look at it as a model, this lower section shows the motor and pump as a combination, energy going in and energy going out, and the efficiency of that system is going to be the ratio of the output energy divided by the input energy. Now let's talk a little bit about what that energy is from the electrical side. So the electricity basics. So what you need, of course, to use electrical energy is you're going to need a power supply. In this simple image here, we've got a battery and a bulb. So this is essentially your flashlight. Now the electrical model for that is a power supply, a switch, and a resistor. And so this circuit here can be representative of many things, including our motor. And so the power supply, of course, is required, the switch is required, and then the load, in our case, whether it's a light bulb, the resistor, or our motor. Now when it comes to electrical measurements, there's basically 3 key characteristics for introductory electric circuits. The batteries or power supplies provide the potential to force or move current in a circuit, and it'll be measured in voltage or volts. And this is similar to the pressure behind a water valve. And so the water analogy can work. Let's take a look at this image here in the middle on the right. So a pump is circulating water around. So it presses it through, it goes through a restriction, and then returns to the pump. So this is just circulating water. And that's very similar to an electric circuit. So the voltage on the battery drives current through the bulb and it returns. All right, so that's the nature of the comparison between water and electricity. It's not ideal, but it's not bad. So the pump provides that potential, it provides that pressure to force the water through. Now, for current in reality is the motion of electrons around a circuit. Right, and so similar to this is the water, the motion of the water around around the pump loop. All right, so the motion of the electrons is measured in actually a unit called amps or amperes, and it's similar to the water being pumped around the loop. Now this restriction is the other key part. So if this restriction were not as small as it is now, there would be less resistance to the flow of the water, and so the obstacles to electron flow develop a resistance, and just like this restriction is an obstacle to water flow. So now the energy in the loop, we can be more specific about this later, but let's talk about the experiences. So the voltage provided by the battery or the power supply is a function, can be related directly to current and resistance, and that equation is shown here on the lower right. So the voltage across any one of the parts, and so in our case our only part is the light bulb or the resistor or the motor. The voltage across that motor is equal to the current flow through it and its resistance. And so if we happen to take the current measurement and the voltage measurement, then we could figure out what the resistance was. And so this can be rearranged and used several ways. These are great equations to write down and try and add to your memory bank. You'll be using them quite a bit. Now, when it comes to the power and energy in the system, the power is the product of voltage and current, and we can check the units and do some of that stuff, but the units are in watts, or another phrase, because it's a rate of energy use, it's joules per second. And so the power is voltage times current, and we'll be taking those measurements during this first week to test our pump when it's not running water, our pump and motor combination. Now, if you're going to measure the energy that is used by the pump, you're going to have to take the power supplied to it and multiply by how long that power is applied. So the product of power and time is going to give us a measurement of joules. And so again, these three measurements, these three equations will help us do most of our work in our introductory circuit stuff. So now let's take a look at the energy output. So the image on the right shows our pump, or a pump, taking water from a tank and rising it, lifting it up to some height. All right, so this is what we're talking about, is what kind of energy is being put into the pump, right? What kind of work is it doing? So how much energy is added to the water by the pump? So the pump adds energy to the water in two primary ways. Potential energy is added because you're raising the water up against gravity, and then kinetic energy is added by increasing the speed of the water. So let's talk about the potential energy first. So any mass that's moving up against gravity, whether you're raising a book from the floor to the table, or raising, in our case, water up and having it exit at the top side of a discharge location, all of these are adding energy to that water. Now, of course, the water falls back down and loses that energy, but we put that energy into the water when it leaves. So the amount of energy is based on the mass and the height, and so that formula for potential energy is the mass of the water times gravity times the height that you move that water. So again, another common physics formula to remember. Now the kinetic energy is the next piece. Any moving mass has kinetic energy, whether it's a vehicle or water. And so as the water exits the top of the tube, it's got speed, and so that's the speed, that velocity is what is used to determine how much energy it has. So the amount of energy is based on the mass and the square of the velocity. And so, and the units are again in joules for each of these, the potential energy and the kinetic energy. So for kinetic energy, you've got 1/2 times the mass times the velocity squared. So the kinetic energy can be found by determining what the velocity is as it leaves the tube and how much water was moved. Now, on the energy and power side, the total energy is found by adding the potential energy and kinetic energy together. While the power represents the rate of energy used, it can be found by dividing the total energy by the time over which it's used. So if we run this pump for 5 minutes and capture all of that water, then that water was, that energy over that period of time will help, that time will help us decide what the power was used. All right, so the amount of energy over the total amount of time divided by the time would give you the power. A little confusing there. All right, so let's move on to the next piece. Actually, for our first week of work, these are the key things that you'll be using. The electrical measurements will happen during week 4, and then during week 7, we'll actually test our pumps with our new impellers inserted in them. So the system efficiency will be measured in week 7, but a primary electrical measurement will be done in week 4. So make sure and go out, take a look at how both experiments are done, how the electrical measurements are configured and measured, and then how the practical part of the test is completed. Spend the time to watch those videos as well.